There we go. How was that? Were you up to something in the dark there? It's like one of these, like a Brian Cox concert, isn't it? All right, hello everybody. So I got delayed by one of my tutors who didn't want to leave the room. So apologies for being a minute late. Right, so the main page. Display. Okay. Look at that, it's all working. Zoom out. Where were we on Friday? We were revising boundary conditions as they apply to electric fields between two different media. Okay, and we applied each of the Maxwell's equations. Okay, as we saw, applied each of them to find out how the electric and magnetic fields, transform themselves across a boundary. And the most interesting one of those was this one, which was complicated by the fact that we were saying that across a boundary, the change in the magnetic field, where we're considering this dotted boundary here, this dotted plane, is the plane in which H1 and H2 were existing. We just chose them to be in that plane to start with. The change between H1 and H2 is equal to the current flowing perpendicular to the plane in which H1 and H2 sit. And that was all fine, except we could only sustain a current in an infinitesimal layer if we have a perfect conductivity in that layer. Okay, so any finite conductivity situation, right? We had to have that the parallel components of H1 and H2 must be the same. All right, so that's where we got to. Now, those are our boundary conditions which relate the electric and magnetic fields. Now again, we're just going to revise these statements. We're going to write them down fairly briskly, because we're just going to later on use these statements as a kind of aide-memoire about how we expect waveguides to operate. Okay. So the first thing we want to do is look at reflection at normal incidence in a classical dielectric. Okay, that's our starting situation. It's the simplest one. And we're just going to build up to all the other situations so we know how to calculate each of them in turn. Okay? So we want to do definitions. Right. Remember that the relative permeabilities and permittivities are always real. Okay? And again, as always, usually mu r for most situations will be equal to 1. Okay? Non-magnetic materials. And as normal, we're going to calculate what happens to a plane wave, an incident plane wave. And I'm going to change my labeling slightly. EI0, incident, is I, with amplitude 0, and again it's going to be propagating in the z direction. So as we conventionally write, the electromagnetic wave has an associated magnetic field. Okay, so that means the boundary occurs at some value of z. That's the boundary between medium 1 and medium 2. This is our interface. Okay, so our interface I'm going to take for convenience to be at z equals 0, obviously. Why would I choose a different one? So now I can draw some axes to show what's going on. I have the electric field pointing in x, I have the magnetic field pointing in y, and I have the direction of propagation in z. Okay, so I have leave yourself a bit of space in between here and the main part, the main axes. So my incident electric field EI0 points that way, and BI0 points this way. Okay, according to the way I've drawn it. So this is my incident wave. Okay, just defining my signs and directions. And I'm going to define my transmitted wave on the other side. So clearly I'm going to relate the strengths of each of these components, EI0, BI0, ET0, BT0, etc. Okay, going to relate all of them together according to these boundary conditions. This is my transmitted wave. And I'm going to do something a bit weird. I'm going to define, if EI0 is positive, I'm going to define a positive value of the reflected electric field, ER0, to be pointing downwards, not upwards. And you'll probably be able to guess why that is. I'm going to keep the magnetic field pointing that way, and you can probably immediately recognise that the reason I do that is that because of the right-hand rule coupling together these two components of the electromagnetic wave, clearly that works if the reflected one is going backwards. And we'll see in a minute that ER0 is more easily defined pointing down than pointing up. Okay? Remember, I've got this is a medium 1 on the left, right, and this is medium 2 on the right. Okay, such that in medium 1 I have a wave number K1, so this is all for the same frequency, isn't it, right? Wave number K1, relative permittivity epsilon 1, which has a refractive index N1, okay? And for completeness, a relative permeability mu1, and this we have the corresponding values in medium 2, okay? And we can couple together K, N, and omega, as so, like so, okay? So the frequency is the thing that remains constant across all these incident, reflected, and transmitted components. So we apply the boundary conditions. Okay. So the first thing we see up our plane wave is there is nothing which is perpendicular to the interface. Okay. There's no components of anything perpendicular. So our boundary conditions are only for the parallel components. Okay. So we can apply our boundary conditions as so. E parallel is continuous, which means that EI0 minus ER0 equals ET0. Now, that was easy. Oops, sorry, there you go. And the other boundary condition was that B parallel over mu, the relative permeability, sorry, okay, is continuous, CTS. So therefore, BI0 over mu1, that's the relative permeability in material 1, plus this time, remembering the sign convention we've just adopted, over mu1, two mu1s there because they're both on the same side, equals BT0 over mu2. All right. So that's very easy, really, isn't it? Just couple together those 6 parts of the electric field. And of course, we already know that the magnitude of B on either side is equal to the strength of the electric field on that side divided by the velocity of the wave. And that's just equal to E times epsilon r, epsilon 0, mu r, mu 0, for whatever values of epsilon and mu happen to be on each side. Okay, so I can relate B and E together on each side. B over mu r equals 1 over c, epsilon r over mu r times E. That's another way to write it. Okay. Okay, so generally, we can now find that epsilon 1 over mu 1, those are the relative mu 1, okay, those are the relative permittivities and permeabilities on material 1, EI0 plus ER0, okay, so that's just taking statement 2, rewriting it in terms of the electric fields, is equal to epsilon 2 over mu 2 epsilon T0. Okay? And then, to make things a bit simpler, we said that the relative permeabilities mu 1 equals mu 2 equals 1. So therefore, N12 with 2 refractive indices are equal to the square root of the permittivities in each of the materials. So that allows me to write down the relationship between the refractive index and the strength of the electric fields and relate them on one side to the values on the other side. Great. This is just churning through, right? So that's what I've done is I've taken condition 2, the continuity of the magnetic field. I've used that to relate the three components according to the sign convention that we just drew. Okay, there's our sign convention. Right. All I've done is just reverse the direction of ER0, and I've worked through to relate the refractive index times the electric field on the left to the refractive index times the electric field on the right. I can now combine that with my first statement, which is up here, about the continuity of the parallel electric field, and I can write down two relations by combining those two things together. I can write down the ratio of the reflected electric field component to the incident one as being equal to N2 minus N1 over N2 plus N1. You probably have seen this before somewhere. And the transmitted component, ET0 over EI0, is equal to 2N1 over N2 plus N1. Okay? Right, so if I know the permittivities, I know the refractive indices, if I know those, I can relate all the reflected and transmitted components. And that just arises from Maxwell's equations. Okay. So clearly, straight away, we see that if N2 is greater than N1, then ER0, the magnitude of the electric field component in the reflected wave, is greater than 0. Right? And we normally, don't we? We normally think of waves incident from a rare medium, one with a smaller N1 value, into a denser material with a larger N2 value, and because we normally consider that, that justifies our choice of the directions for our sense of the electric field. Okay, so just to remind ourselves, we were saying that our incident wave looked like this, and our reflected wave looked like this. Okay, going the other way, of course. Can't do the wiggly line going the other way. Where ER0, so if N2 is greater than N1, then ER0 is positive for a positive EI0. Right? That's the reason why we draw it that way. So just means your signs are a little easier to keep track of. Okay. Zoom that out slightly. Still see okay like that? Give it a little bit more on the screen at a time. Okay, so you can do the same basic rigmarole to show that BR0 over BI0 to relate the magnitude of the magnetic fields to each other, so we've got the electric fields above, well, the reflected components are just the same as they were before. Okay, when you work it out. It's the transmitted magnetic field strength which is different. And this is often missed. It's equal to 2N2 over N2 plus N1. Okay, so notice that difference. For the electric field, it's N1, and for the magnetic field, it's N2 when you calculate it. Okay. And again, if N2 is greater than N1, then all these quantities are positive values. Okay? So if N2 is greater than N1, then ER0, ET0, BR0 and BT0 are all positive if all the incident values are positive. Now obviously the direction of B that you need to have, well that's pretty, if you know the magnitude of E and you know that it's, you know whether it's being transmitted or reflected, then clearly you can deduce anyway the direction of B. It can be deduced. Okay. Directly from consideration of what E cross B, which way that points. Okay. Okay. Now those are the electric and magnetic field components. I always have to let you write them down. I know I've briskly gone through this because it should be quite familiar, at least the concepts particularly. Okay. The extra step was our statement about the Poynting flux, okay, because we know that the energy in each of these three components, this is the incident, reflected and transmitted components, the energy flux, the flow of energy per unit area, per unit time, is given by the value of the Poynting vector, the Poynting flux. Okay. Obviously that's just equal to 1 over mu 0 E cross B. Okay. In other words, it's the magnitude of the electromagnetic fields together. So I want to calculate the degree to which I have reflection and transmission, and those are governed, of course, by the reflection and transmission coefficients. So the reflection and transmission coefficients, which again you've seen before, those are conventionally labelled R and T, and remember they're defined for the intensity rather than the magnitude of either the electric or the magnetic field. Okay. Well, clearly the reflection coefficient is simply equal to, slide up a bit, it's equal to ER0 over EI0 times BR0 over BI0. So that's going to be N2 minus N1 squared over N2 plus N1 squared. Okay, just multiplied those two ratios together, and the transmission coefficient is equal to 4N1 N2 over N2 plus N1 squared. So everything fits together because R plus T equals 1, doesn't it? Okay, so R plus T equals 1, and remember this was all for a ordinary classical dielectric. Okay. Now I realise I've made you jump through that quite fast, okay, but it should be straightforwardly familiar. So remember, the important thing to realise here is where the N1 and the N2 arose from. N1 arises because of our consideration of the continuity of the electric field across the boundary, and N2 appears in that formula because of the magnetic field. Okay. Okay. So those two numbers are the ratios of the transmitted amplitudes of the fields. Okay. Now we should fill out that concept with a statement about how phase changes at reflection, which hopefully you can see fairly quickly, happens as follows. Here is some boundary, okay, and we have N1 on the left and N2 on the right, such that N2 is greater than N1. Okay, so we can have an example, I don't know, e.g. Air on the left going into water on the right, for example. Right. Obviously water is not usually vertical, but you know, you can rotate your axes if you like to make it gravitationally possible. And of course, because N2 is greater than N1, we know therefore that at any given instant the electric field in the reflected wave points in the opposite direction to the electric field in the incident wave, and they're both oscillating up and down. So here is the incident wave coming in, like so. Try and get it to just give me a finite value, just cheat a bit there, it's a finite positive value, okay, at the boundary. That's my incident wave going this way, and therefore the electric field in the reflected wave must be equal and opposite, so it's got to be the same distance underneath, and it should, if I can draw it right, there we are, look so, okay. Would go wrong. That's not too bad there. Okay, there we go. That's my reflected component. Okay, and the important thing here is that those two electric fields are equal and opposite to each other. Sorry, opposite to each other, not equal and opposite to each other. But their phases are exactly pi apart. Okay? There is a pi phase change, so they're not equal and opposite, sorry. Obviously, because one can be smaller than the other, right? Okay. That's if N2 is greater than N1. However, if N2 is less than N1, then obviously the sign of ER is now opposite, then therefore ER is in the same direction as EI, therefore no phase change. Okay? No phase change. Okay. Excuse me. Slide that up a bit. So these concepts you've seen before. So just to recap, what we've done is we've gone through the continuity of the electric and magnetic fields at the boundaries, and in the case of a classical dielectric, which is non-magnetic, where we can relate the refractive indices to the permittivities, we can explicitly calculate the magnitudes of the electric and magnetic fields in the transmitted and reflected components. We can relate those to the incident ones, and we can directly derive that they're from a rare to a dense transition, such as this one, then we have a pi phase change in the reflected component. But if it's from a dense to a rare situation, N2 is greater than, if N2 is less than N1, then there's no phase change. Okay. Time for a few examples, just to fill that out. An example you see coming up in exams fairly often is the situation of a thin soap film, so it's probably worth writing that down. Okay. A thin soap film. What do we mean by thin? The thickness of the soap film is much less than the wavelength of the light which is passing through it. So we'll draw a thin soap film like so, like a bubble or something. So this is a small portion of a bubble, so it's more or less flat, some thickness T, okay? And just to make it a little clearer to see, we'll draw the incident component at a slight angle, just so we can see it, right? So it's not really at an angle, still considering this to be effectively normal incidence. And of course what we're interested in here are the two components, the one that comes off the air to A transition. Okay? So clearly N inside the soap film is greater than the air either side, obviously. So that's the A coming from there. We also have another component, which is when you get reflection from surface B, gives you the B component of the reflected ray. So you can see that there are two different situations. So ray A is reflected by surface A, okay, reflected at surface A, whereas B is transmitted at A, so we need to take account of that that change. Okay, transmitted at A, it's then reflected at B, and then transmitted again. Okay, again at A. So there's three transitions between those two refractive indices. Some are going denser and some are going less dense. And if you work it through, you can see that overall ray A has an overall pi phase change. There's only one bounce, and it's from N1 to N2, so N2 is bigger than N1, so there's a pi phase change. B needs a little bit more thought, but you can convince yourself that there's no phase change at all. Okay. So our statement here is that these two electric fields and these two reflected components, one of them is pointing up while the other is pointing down, right? So therefore, there's destructive interference. Okay. Now we've just considered destructive interference for normal incidence, and we can say that's the case because T is much less than lambda, so there's no significant phase lag in between when going from A to B, and that will remain true over a significant range of angles. It will also be true over a significant range of wavelengths, as long as those wavelengths are all large in comparison to the soap film thickness. So therefore a soap film appears dark. That's example number 1. Okay. Now the other 2 examples are more mundane, but they're just to remind you of the typical values that you might get, okay, when you consider optical and radio wavelengths. Okay. So we have clean glass and visible light. Okay. And the visible light has a wavelength of the order of a micron, maybe half a micron or so. Air, to all intents and purposes, has a refractive index of 1 or very, very slightly greater than that. So that's our rare medium. And when light falls upon glass, well, glass has a variety of refractive indices with visible light, but let's say 1.5 is not uncommon. Okay, so it might vary from 1.3, 1.4. If you've got slightly more expensive glasses, it might go up to 1.7, even 1.9 if you pay the extra pounds. Okay, I don't. These are 1.7. All right, then the amount of transmission from the air into the glass is as high as, in this case, about 96%. Okay, just calculate it, show you can do that. And very little reflection, about 4% reflected light. So we should compare that. Let's think of another situation, water. We'll think of water when long wavelength radiation, this is our, and we're talking about radio bands, this is trying to send signals to a Russian submarine. Okay? Imagine you're a British spy and you're trying to interfere with some kind of, I don't know, some process or other. So you're sending signals to a Russian submarine off the coast and you're using radio waves of 100 megahertz. Think how much of the signal will get to the submarine? Well, at those wavelengths, the refractive index of the air still equals to 1. Water can have a refractive index as high as 9 at those wavelengths. Okay, so it might be 1.3 at visible wavelengths, but it might be much, much higher. So that's a very large permittivity, and that's a permittivity in the 30s. Okay, and in that situation, there's an appreciable amount of reflection. Okay. The transmitted intensity might be as little as 30% or so, and the reflected amount might be as much as 2/3. Okay, so quite a lot of the power gets reflected off. Okay, okay, so that's our dielectric situation. I'll just pause for a moment. Okie dokie. Now, of course, here in the first situation of the dielectric, we had real values for the permittivities and permeabilities. Now, that's not the case anymore for conductors. So they're more interesting. That's why we started with the easy situation. And we'll look at angles again in a minute. Has everyone got everything down? This is all in the notes, as you know, right? So if you miss the odd line here and there, you can fill it in later. Okay. But I know it's also useful to write as you go, right? Some things tend to go better into your head if you're writing them down at the same time, don't they? It all depends on the speed, doesn't it? I don't know. Okay, so normal incidence on a conductor. Things can be a little bit different here. Normal incidence, and we're going to consider reflection from a conductor. Okay. And again, the basic idea will already be familiar to what we're doing is we're just revisiting it with our boundary conditions. So we're going to be considering, obviously, our conductor. We're going to consider together a plasma and a metal. Oh, I didn't mention Langmuir waves. Remember Langmuir waves? We said that plasma oscillations are known as Langmuir waves. It's because the word plasma was first coined by Irving Langmuir in 1928. And he considered it, some people say, by analogy with the kind of the conglomerates of stuff that flow in blood. So it's not accidentally that's called a plasma by comparison with blood for some reason. It's meant to be a quasi-neutral material, okay, composed of different pieces. So here is our situation with an incident plane wave onto the surface of a metal, and obviously, or a plasma for that matter. Okay, I'm going to denote its wave number Ki. That's equal to 2 pi over lambda, and I'm going to denote N1 in the rarer medium. This is going to be assumed to be a dielectric, and N2 in the metal Well, this is going to be complex valued, isn't it, as we saw before. Okay. So that complex nature of the refractive index tells us something. Let's write down simple-mindedly what the reflected components and transmitted components are. So just as we had before, ER0 equals, because nothing has changed there, these are just the continuity equations at the boundary that are giving rise to these components. Okay, so write them down just as we did before. Okay, so obviously I don't need to write down all of them, I'll just write down the electric field ones, because the magnetic field ones, obviously by analogy, with a slight change in the ET0 value. So the first thing we notice is ER0 and ET0 are now complex valued because of the complex value of N2, which tells me that there is a phase shift. There's some phase shift with respect to EI0. Okay? We already know that. That's our general statement. And we're going to do the same thing we normally do. We're going to consider some limiting situations. So the first thing we're going to do is, let's pick something. Low frequency and a good conductor, say. Let's do that one. Okay? Because it happens to be the one that's written over here. Okay, low frequency and a good conductor. So, we saw before, we could write down explicitly what N2 was in this situation. It was approximately equal to square root of minus I sigma over omega epsilon naught. Okay? And we could equivalently write that down as sigma over 2 omega epsilon naught 1 minus I. Remember that square root of minus I is 1 over root 2, 1 minus I. So we can write that down in the following form, just to make it a little clearer, rather than having to carry around that square root term. Let's write it down as N2 equals alpha 1 minus I, okay, where alpha is that what's in that square root. Okay. Make sure I don't miss any of the terms out there when I'm scribbling out. And if it's a good conductor, alpha is much greater than 1. So therefore, let's write down the magnitude of the reflected wave, R, is equal to the size of N2 minus N1 squared over the size of N2 plus N1 squared. Okay. And just write that down in terms of alpha. It's alpha minus N1 minus I alpha over alpha plus N1 minus I alpha. Okay? So see if you can show that that is true. Okay? And I can rearrange that to be 1 minus N1 over alpha squared plus 1 over 1 plus N1 over alpha squared plus 1. Notice the minus and the plus. Okay? Minus above, plus below. Right? And I can write that out as 2 minus 2n1 over alpha plus n1 squared over alpha squared over 2 plus n1, 2n1 over alpha. Yeah, it should all be symmetrical top and bottom, plus n1 squared over alpha squared. Okay? Just work your way through, just follow those minuses and pluses of the numerator and the denominator, and then we observe that because alpha is much greater than 1, then this final term here is smaller than the others, so we can get rid of it. Okay. So if you look, you can cancel out the 2's in the numerator and the denominator, that's easy, and I can rewrite this in a slightly more digestible form. Okay, so that R is equal to 1 minus n1 over alpha in the numerator, and then 1 plus n1 over alpha to the minus 1 in the denominator, and that is approximately equal to 1 minus 2n1 over alpha. Okay. So remember, this was for alpha is much bigger than 1. In other words, omega epsilon 0 over sigma is much less than 1. That's our statement. Okay. Right. So for this situation, which is the metal, we can write down the reflection coefficient as being approximately equal to 1 minus 2n1. That's the refractive index in the less dense material. It's probably 1, isn't it? Right, n1. And then we explicitly can write down the effect of the conductivity, sigma. Okay. So remember what we've got here. This R is an optical property. We're writing it down in terms of an electrical property on the right. And obviously we don't need to work out T explicitly, we just already know that it's 1 minus R, right? So therefore that must be equal to 2n1 square root of 2 omega epsilon naught over sigma. Okay. Right. So we can take these electrostatic properties, which is the vacuum permittivity and the conductivity, and from those we can work out what the optical properties are. Right? A great triumph of Maxwell, I would say. So a common thing to consider would be some metal upon which electromagnetic radiation is incident from air. So they're all much the same, aren't they? If you look up the conductivities are optical wavelengths are usually about 10 to the 8 per ohm per meter. Okay, so it shouldn't matter a great deal, should it, what metal we choose, as long as they're reasonably conductive. So in air, N1 is pretty much equal to 1. Okay. The conductivity, well, in this case, is about 6 times 10 to the 7 per ohm per meter. Okay. And again, pull out your calculators, just show you can calculate these numbers quite happily. Omega, well, let's pick an interesting one. We'll pick lambda equals 25 microns. And again, I remark that when we describe this lambda, we are assuming this is the free space lambda rather than the lambda that resides inside this different material. Okay, so this is not otherwise described. You should always conclude that it's the free space lambda. Okay, 25 microns is a bit longer than 1 micron, right? 1 micron is visible-ish. A few microns is infrared. This is further than infrared. It's called the far infrared, FIR. As you'll see. Okay. It's optical enough. Okay, just did it for interest. So omega, in this case, if you're working out, 7.4 times 10 to the 13 per second. And in this case, the transmitted component is only about 0.9%, and the reflection coefficient is something like 99%. Okay. Okay. So those are the lower frequencies. Now I chose far infrared because there's something else going to come along. What else is coming along? That happens at high enough frequencies in our conductor. What we've been discussing before. Plasma frequencies. Okay. So, then we'll look up how many red metals there are. Did you find any? If we ever see a yellow metal, say brass or gold, right? Brass is an alloy, gold is not. Brass doesn't have any gold in it, and yet it still has a yellow colour. It must have it must be composed of another metal that also is non-silver. Okay. So as far as I'm aware, there's only two common metals that are not silver in colour. One of them is copper and the other one is gold. So let's see why they are coloured, whereas all the others are not. We look at higher frequencies in a good conductor, and we recall from our previous section we could write down the relationship between the wave number k in a system that has mobile electrons, whether a plasma or a conductor, and we can relate that to the frequency of the wave that's trying to propagate through that material, and relate that to the natural plasma frequency, okay, as so. All right. And remember, we had two situations that were of interest. And again, have a look in the back end of section 3 at that figure that shows the boundary line. Remember, I asked you to see if you could plot that line. When the driving frequency, when the incident frequency is much less than omega p, then the electromagnetic wave cannot propagate through the plasma, and therefore it is an evanescent wave. Okay? So this is a situation in any metal where the incident frequency is lower than the plasma frequency. In that situation, we have the following things, right? The permittivity is less than 0. K becomes imaginary. T equals 0. And R equals 1. Exactly. Okay. When omega is greater than the plasma frequency, then the plasma can support the propagation of electromagnetic radiation. Epsilon is greater than 0, K is now real, and T becomes 1 and R becomes 0 at a large enough omega. Okay? So this must be the reason why some metals are coloured and others are not. Let's see if we can show that by means of a suitable plot. So here is, so I'm going to mess with you a little bit by doing this as in terms of wavelength instead of frequency to get you to swap between those two. And we look at the reflection coefficient R, because that's the light we're going to see, isn't it? Is a reflected light from the surface of any of these metals, and clearly it's going to vary between 0 and 1. So let's draw that in. Okay. So the first thing we can draw is a situation of any silver metal. Let's pick the canonical silver metal, which is silver. Okay, and let's put some wavelengths: 400, 600, and 800. Those are the ones that our eye can see, and those must all be being reflected, right? And that tells us that the plasma frequency must be, well, the driving frequency, well, let's see if we can draw that carefully. We'll draw at this upper end here. Okay, in this situation, this is larger wavelengths, so smaller frequencies. So in all these situations, frequency must be less than the plasma frequency. Okay, and that's a situation where I get reflection at these wavelengths. So these are all the smaller frequencies, the longer wavelengths. But at some point, the plasma frequency, which must be presumably now lying around here, okay, at this point here, this must be where the plasma frequency is, and around about that point, the reflectivity drops off. Okay, so in this situation here, omega must be greater than the plasma frequency, but that's okay because our eyes aren't sensitive to it. We see these wavelengths, these wavelengths, these wavelengths. We see uniform reflection across all those wavelengths, and hence this is the situation that pertains to a metal such as silver or aluminium or any of those other ones. Okay. Clearly the plasma frequency must be different in a yellow metal, let's say gold. Now gold's a little bit more complicated but the basic idea is sound, right? The plasma frequency must now be up here, it must be lower. Okay? So the plasma frequency is lower. So now instead of having uniform reflection at all wavelengths, blue light is partly transmitted. Okay? So the blue light is partly transmitted because its frequency is above the plasma frequency, and therefore gold is yellow in colour. Okay? And so on for the things like copper. Okay? So just to help you, omega increasing in that direction, isn't it, of course? All right. Okay. So that's why some metals are coloured, and not many of them are, which does imply that for most metals the plasma frequency falls down here rather than up there. Okay. So that's normal incidence. As we normally do, as I normally do, I'll introduce the next section on Friday just to get us into the mood. Okay. I'm not sure what kind of mood you want to get into, but there we are. I'm trying to go through this stuff fairly briskly because you've seen it before. This is the bit where it's a little bit more fiddly to keep track of these electric field components. The normal incidence is pretty straightforward, right? Oblique incidence, which is what we're going to do now. So just the bit we're going to get to in a few minutes is the bit we'll just have to revisit it on Friday just to make ourselves happy, okay? So again, we're going to do dielectrics first, okay? So reflection. Yeah. Probably all of us would probably say we want to be out there having that party, don't we? But never mind. Well, you can go there in 5 minutes, all right, and you can see what they're up to. Maybe they've gone on to even better party by then, but there we are. Okay, at least the door's shut today, eh? So reflection and refraction from dielectrics, okay, because we're seeing that obviously they're the same things, aren't they? Okay, so if we have oblique incidence, we can get a change in the angle. So again, very, very familiar concept to you. Propagating in Z, we have some direction X that to define, you know which way Y is, it's into the page, or out of the page. I'm just indicating by means of the hatches, that's the more dense material, and the difference here, of course, is that we now have the possibility of an incident wave at an angle. So I'm going to call that wave vector Ki now, and I'm going to draw Kr. And so far, this is part of our derivation, we're not assuming that theta I equals theta r, we're going to show that it is. So I'm going to label them as different angles, we'll show momentarily that they will be the same. Okay. So we have a vector Kr. So Kr has a direction and a magnitude, of course, and we have another angle theta t that goes with the transmitted wave vector Kt. Okay, different directions, different wave numbers, but again we have medium 1 and medium 2, left and right. And in each particular material, we can say that omega over k equals c over n, i.e. that k, the wave number, the magnitude, its magnitude, which of course determines the wavelength for a given frequency, equals n omega over c. Okay, just to remind ourselves, and that's true on either side. Okay. Now you can see I've written i's everywhere. So just for this section, we're going to replace the complex I. Okay, so let's just otherwise you'll have different i's everywhere and get confused. We're going to write square root of -1 equals j just for this section. Okay, that's just a notation change. Okay, so let's just plough through, and we'll write down. So I is incident, of course, right? So let's just plough through. We're going to write down what these three components look like. We've got the incident vector EI. Vector value has a direction EI0, so it now has some component in the direction of Z, doesn't it? And it has a time variation e to the j omega t, so that's our new I value there. Okay, Ki dot r. Okay, so Ki dot r is how far I've moved with respect to r equals 0. So that's the phase, that's the spatial phase there. Okay. And I've got exactly the same things for the reflected and transmitted components. Okay. Obviously, everything goes up and down at the same time, right? So the omega t's, j omega t's are all the same for all the components, and that's going to be crucial in working out what we're doing. KRR, but the KR and the KT values, they can all be different to each other in principle. ET equals ET0, okay, e to the j omega t minus KT dot R, okay. And of course for all these electric fields, we've got BI equals 1 over V, where V is whatever the velocity is in that particular medium, KI hat, which is the unit vector in the direction of propagation, crossed with the electric field, okay? And that's true for all the components, okay? Now, the key thing I want to get across here is we're going to apply a continuity. So, the continuity of B parallel and E parallel at the interface. Okay, remember the interface is at Z equals 0 like it was before. Okay. This demands that all the phases are equal. Okay. This is the important statement. This is the bit that's a little fiddly to accept at first, but what I want you to do is just go away and think about it and just convince yourself that it is true. Okay. So that means the phases. Okay, that's those components ki.r, kr.r, and kt.r are all the same at z equals 0. Therefore, I can write down the following statement, which is where we'll finish today, and then on Friday we'll look at its consequences. Okay. r.r equals 0. Okay. So that's where we'll stop today. The statement that all the phases, because the reason that has to be the case is that these electric fields must all add up and be consistent with each other, and if they're all changing with time, they must all go up and down together while still satisfying these continuity conditions at the boundary. That's what makes those phases match up. Okay, so I'll leave it there for now, and then we'll come back and we'll see what the consequences of that are when we look at this on Friday. Okay.